Okay, so we're starting chapter 4. This is chapter about regular rings. And complete intersections. Not a huge chapter for just a couple of weeks. So first section, I'm going to collect basic facts about regular rings. So the plan for regular rings, now in the first section I give a definition, check some elementary properties and one non-trivial property. And then the next goal is to show that every regular ring is a U of D, unique factorization domain. To do this, we first show that every regular ring is a normal ring, so next section will be just some things about normal rings, and then after that we will have a section about unique factorization domains, and in particular prove that every regular ring is a unique factorization domain. Okay, definition. As usual, two parts for local situation and for general situation. So a local Noetherian ring, or M, is called regular. Well, for shortness in the literature, people sometimes write R, L, R, regular local ring. And this definition, of course, includes the assumption this is Noetherian. So any R, L, R is L and R. If dimension of R is the same as the embedding dimension of R. It's the standard definition. The same definition, for example, is used in Natia McDonald, where they prove some elementary properties of regular rings.
What is ending?
You asked this question last time, so maybe let me write this. So the embedding dimension, so this is just a comment. Embedding dimension, so I'm going to call this edim. Sometimes people write imdim, but edim is shorter. So for local ring, this is by definition the dimension of the vector space of the M modulo M squared. So this is the dimension of the risky cotangent space at the unique close point of this.
Yeah, so we assume that everything is Noetherian.
Yeah, yes. To talk about regular rings, I assume everything is Noetherian. And that's the standard assumption. By definition, every Cohen-Macaulay, every Gorenstein, every regular, every complete intersection is Noetherian. Yeah, so that's the formal definition. So you can think about this as again the dimension of the cotangent space. And in these situations, you claim that the dimension of the cotangent space is kind of the same as the dimension of the variety. And so this is kind of the standard definition of regularity, the dimension of inside. But algebraically, you can also say this by E, ED, or is the number of elements in a minimal generating set, minimal generating set of the maximal ideal. So that's an algebraic kind of just restatement of what we define. Of course, we have clearly this minimal generating set of M. This is precisely what under the map from M to the M modulo squared goes to the basis of this vector space. Or you can just take a basis of this vector space and lift this to the minimal generating set of M. And geometrically, you can think about this embedding dimension as kind of you have this singularity, which is very hard, and you're interested in what kind in what space you can embed this with a minimal dimension of this ambient space, right? So some singularities, say you can say take one-dimensional singularity, you can realize this in the say this is a curve, you can embed this into the plane, then the embedding dimension is 2. If this is only a 3-dimensional space, then the embedding dimension is 3, etc.
So how to understand such construction?
Well, in fact, we will go into return to this when we discuss complete interceptions. You need to actually, to make this completely correct, you need to take completion, so we will discuss this next week with a little bit more details for complete intersections. Yeah, but for our purpose to prove theorems, algebraic theorems, the formal definition and this little interpretation in terms of the minimum number of generators of M is enough. Yeah, and the second part of the definition, and theory ring. Theory ring R is called regular if localization at any maximal ideal is regular. Yes. R L R for any M in the spectrum of R. Okay. Well, it's kind of separate definition, so I don't know, maybe I formulate this as another definition. I don't want to write this as a part 3 because I'm going to define a different notion. So, if Rm is a regular local ring, then let me choose generators for the maximal ideal. Right, so then this number of generators M is the same as the dimension of the ring R. And this sequence, so sequence x1 x10 is called regular system of parameters.
Извините, тут решил зайти на цветную трансляцию, и, судя по всему, транслируется только датовская. А вы знаете, как можно изменить?
Тогда там какие-то вот есть какие-то настройки, кто-то поменял. На том экране видно, что происходит. Ладно. Что-то куда бы я не нажимал, ничего не меняется. Не приближается, не удаляется.
Мы зайдем, потому что приближение удаления это камеры, а это просто оно как-то зафиксировало доску.
Да, человек. То есть тогда мы действительно видим, где происходит трансляция. Ну, тут 4 кнопки, я на все нажал, ничего не изменилось. А вот здесь есть видео подмены. А, нет, это просто показывает видеокоммутацию. А вот тут еще такой есть кнопки. Так. А, это теперь на видео просто включилась камера, и теперь мне нужно ее...
Да. О, отлично. Вот. Супер. Надо, кажется, как обычно.
Да, это называется, если что, общий вид 2, и еще камера должна быть пригодится. Yeah, so just let me check that you remember what's the system of parameters for any local material ring. What's the definition?
It's the like the ring of the ideal.
Yeah, you can say that if you generate the ideal by this sequence, then this is M primary ideal. Equivalent formulation would be that if you take a quotient by this ideal generated by this sequence, you'll get something of group dimension 0, or in other words, of finite length. And so, and you can notice that in general, for any system of parameters, what you generate is not necessarily maximal ideal, it's just something inside maximal ideal, which is M primary. What's important in the regular thing, and this only exists for regular rings, that you actually generate the maximal ideal itself. Okay, so first proposition. So first proposition is quite standard. I don't want to prove it, so let's leave this as an exercise for the seminar for the next week. But yeah, in fact, it's quite easy, just a bunch of restatements. So let me assume that Rm is a regular or local ring. Let me fix dimension. So D is dimension of R. Let me assume that this is at least 1. And we have several elements, x1 up to xi inside maximal ideal. And then for these elements, the following 3 conditions are equivalent. So first, the sequence of elements x1 up to xi is a part of regular system of parameters. Okay, it means that you can just add several more elements, n minus I elements, and you get a regular system of parameters. 2, that this is, if you look at the classes x1 with a bar, xi with a bar, where bar just means that we'll be taking classes in the M modulo M squared. In M modulo M squared. So these classes are linearly independent. And 3, if you take a quotient of R by the ideal generated by these elements, then this is again irregular, so is regular local ring. And we can say even what dimension of this thing is, so of dimension, of course, D minus I. I think maybe just one implication is not trivial in this statement. So anyway, so this is exercise for the next week. Okay. So theorem that Rm be a regular local ring. So then R is a domain. So we want to show that one of our goals to show that it's a unique factorization domain. Of course, the first thing is to show this is just a domain. Okay. So the proof is by induction on the dimension. So by induction on the D, which is dimension of R. Okay, so let's look at the case when D is equal to 0. Well, then this means by the definition of regular rings that the maximal ideal is just a 0 ideal. So then maximal ideal is just 0 ideal. So R just a K, and this is a field. So that's a domain. Actually, well, I just want to emphasize, and even as an example, what's a zero-dimensional regular ring? It's a field, quite simple. Of course, for other classes, for Cohen-Macaulay and for Gorenstein, the characterizations are much less trivial. So let me do case of the dimension 1, because essentially the proof for dimension 1 is the same as the proof for the step of the induction. So let's say that dimension is equal to 1. Now, by regularity, we can assume that the maximal ideal in this case is generated by one element, which I'm going to call x, and we can take a prime ideal inside the maximal ideal, of course, and which is different from the maximal ideal. So the maximal ideal in this case has height 1, so this prime ideal P has height 0. So in other words, this P is one of the minimal prime ideals. So what we want to show, to conclude that this is a domain, we want to show that this minimal prime ideal is actually a zero ideal, that this is a domain. Okay, so let's say that we have some y in this prime ideal, and well, since this is P is contained in M, I can write this y as a product of the R and X. Trivially, right? So then, let me say that since I know that P is not equal to M, so the element X is not in this prime ideal P, and since I know that the y is in P, and this is a product of the R and X is not in P, I can conclude that R is in P, right? P is prime. Okay, so R is in P, but this means what we showed, well, we can maybe write it here. So this computation shows that the P is the same as XP, right? So any element in the P can be expressed as X and some other element in the P, so this gives you inclusion in one direction. Of course, inclusion of the XP in the P is a trivial inclusion. But, well, this is not linear ring, so P is finitely generated. So in particular, if we apply Nakayama's lemma, we can conclude that P is 0. So P is 0, hence R is domain. So this is the proof in the one-dimensional case. Okay, now let's do the induction. So if D is greater than 1. So let P1 up to S be all minimal primes. Well, first of all, I claim that M is not contained in the M squared union is the union of these PIs.
Is not?
Not contained. Yeah. Can you tell me why this is not contained in this union? No, suppose it is, right? And of course, just by looking at the right-hand side, the first thing that comes to mind is to apply the prime avoidance, right? So here, the ideal is a prime. So if M is contained in the M squared, right? So then it means that if inside, it means that the quotient of the M by the M squared is 0, which is not the case. The dimension is positive. And the other possibility is that the M is contained in one of the minimal primes, but that's again not possible because the height of the minimal primes is 0 and the height of M is positive. So this is prime avoidance, and M is not equal to M squared, and is not equal to one of the minimal primes. Okay. So then we can claim that the root element x in the maximal ideal such that, well, x is not in the square of the maximal ideal, and also x is not in the minimal primes for pi for all possible indices 1 to x. Okay, so then R modulo this element is regular local ring, right? So this is, for example, applying the previous proposition. We have an element which is not zero modulo m squared, in other words, not contained in the m squared, hence quotient by this element give you a regular local ring. But of course the dimension of this thing is d minus 1, right? So by the induction hypothesis, we can say that the R modulo this element is the domain, and so this is a domain, and if the quotient by an ideal is a domain, it means that this ideal is prime. Okay, so this principal ideal is prime. So, since this is prime, it contains one of the minimal primes. So, this ideal contains one of the minimal primes. Say pi, or some index I between 1 and s. Well, let's say the I is contained in the x. But then we can just look at this argument that we've done in one-dimensional situation and just repeat this argument. So, then the I is 0. Same argument as for d equal to 1. Right? But it means that, in fact, all these minimal primes ideals, they just coincide that they just all equal to 0 ideal. So there is unique minimal prime which is 0 ideal, hence R is the domain. So that was statement this is the domain. Now let's relate two notions. We have a notion of a regular system of parameters. We also have a notion of regular sequence. Let's see how these two things are related. So let Rn be a local native ring. Let's, as before, fix the dimension. Assume that the dimension is at least 1. Then R is regular if and only if the maximal ideal M is generated sequence. And moreover, every regular system of parameters is a regular sequence. So of course in this statement I'm talking about regular sequences for just for the ring R, all these regular sequences are inside maximal entropy. Okay. So let's go in one direction. This is the easy direction. So here I know that M is generated by some sequence with D elements. So this is regular system of parameters. Now we use the previous theorem, and we can say that say since R is a domain, say we can look at the first element x1, and this is our regular, not a zero divisor. Of course, any element is not a zero divisor. And then just continue doing this, right? Well, you look at the quotient by the x1. This is again regular local ring, right? Hence, you can say that this quotient by the first element is domain, right? Hence, you can take the plus of the x2 modulo x1, this is again regular, etc. So let's say R modulo x1 regular, etc. So you continue and you get that this is a regular sequence. And in particular, you can see that this also proves this moreover part, that every regular system of parameters is a regular sequence. Exactly the same proof. So this finishes proof in one direction. So in the other direction. So let's assume that we have a sequence x1 up to xn. This is, so let this thing be a regular sequence. And we assume that M is generated by this regular sequence. Notice that this, I'm using different index. This N is not the same as the dimension D, right? So D is dimension, N is the number of elements in this regular sequence. Well, but one thing is clear. I hope that this is clear, that there is an inequality that D is less or equal than N. Can you explain to me why D is less or equal than N?
Just because of these dimension. Well, like cool height theorem, like then M, then the height of M is less or equal than N, and height of M is dimension in local ring.
Yeah, but pro height theorem, it will be something like if you take an ideal gerund by this n elements, M will be a minimal prime over this ideal, right? So the height of M, which is dimension, which is exactly D, is, yeah, so this is less equal than it. Yeah, the whole Gross height theorem definitely works here, but I want to say this is just a direct consequences of the dimension theory for the local theoretics, right? Because so this D is the dimension, right? And we know that the dimension we can compute not just as a crude dimension, but the least number of parameters, right? So which generated the least number of the number of parameters in the system of parameters, right? So this thing is definitely a system of parameters, right? So the quotient by this thing has finite length, so length 1. But this is probably not the minimum number of parameters, so potential minimum number of parameters, which is dimension, is bounded by this inequality. So the goal is to show that actually D is equal to n, right? And if D is equal to n, this is precisely the condition that this is a regular ring. So what we actually need to prove is that there is an equality in the other direction. Okay, so let's again do this by induction. So if n is equal to 1, so in this case we can set R bar to be R modulo x1. There's only one element here.
Isn't the equality in the other direction obvious because the depth is not more than the dimension?
It's true, it's regular, it's the depth. It's more equal than,
Yeah, what are you saying that the depth?
Always depth is less equal than dimension.
That's equal than the dimension, sure.
Yeah, but then depth is larger than n.
But let's see. So the depth, so the dimension is d, right?
Yes.
And the depth of R is the length of the maximal regular sequence. So in particular, definitely there is a inequality like this. Yeah. So this is the maximal regular sequence. This is just some particular regular sequence. So there is this inequality, and n is less or equal than the depth. Yeah, I think this makes sense. But why I have some complicated proof for this? Yeah, so n. Yeah, I think this works. So then we have inequality. So we don't need induction. We just say that by the dimension theory we have one inequality, by this kind of general observation that the depth is always less or equal than the dimension, we have the other inequality, hence the dimension is equal to the n, hence R is R L R. Let's discuss this. How do you know that if the D is equal to n, then this implies that the ring is regular?
Because they were generated by D elements.
Precisely, yeah. So that's a quite easy observation. Okay. Well, that's interesting. I missed this very simple proof. I kind of have an inductive argument that was just the close height theorem, but it looks like I don't really need this. Yeah, okay, so maybe let's derive a couple of simple observations from this theorem. So first corollary is that if you have Rm regular local ring, so if this is true, then we immediately see that the associated gradient is isomorphic to the polynomial ring from some variables, and number of variables is precisely the same as the dimension. So here D as before is dimension of R. Well, this follows immediately because we proved this theorem when we characterized regular sequences and quasi-regular sequences. We proved that this is true for quasi-regular sequences. This is regular, hence quasi-regular. So this is one observation, simple observation, and the second quite simple observation that any regular local ring is of course Cohen-Macaulay. this is not just Cohen-Macaulay, but Gorenstein. And in fact, even better, this is complete intersection. But to prove this, it will be more or less clear that any regular is complete intersection. In fact, the statement that we need to prove that the complete intersection is Gorenstein, but we will postpone this until next week. It's also not a complicated theorem. Yeah, okay. So this is another quite simple theorem. And now, finally, we have a not so trivial theorem. Maybe one of the key theorems that we're going to use in this chapter. So this is due to Vasconcelos. I think this is around 1969, probably. So Vasconcelos is one of the, I would say, one of the best commutative algebraists of the 20th century. And our century. He's still writing papers, but he's quite old now. I think originally he's from Mexico, but working in the United States. He wrote quite a lot of quite interesting papers, especially if you just want something to read about commutative algebra, which is kind of interesting and nice. You can try to read papers by Vasconcelos, especially his early papers. I think it's much easier to read and understand. For recent papers, of course, I built on quite non-trivial techniques. Okay, so the statement is the following. Let's assume that Rm is local Noetherian ring. I is some ideal. And for this ideal, I have two assumptions. So first assumption is that the projective dimension of this ideal is finite. And the second assumption is that if I look at the quotient of the I modulo I squared, then this is free R modulo I modulo. Okay, so under these two assumptions, maybe let me formulate this as follows. So if we have these two things, then I is generated by regular signals. Well, I don't know about you, in your experience and your days, but for me, this just statement as a just this statement without any consequences is already quite interesting. It's also some geometrical meaning. For example, it means that you consider some variety inside variety. I modulo I squared is the conormal sheaf. Here the claim is this is kind of trivial sheaf. Then you can claim that this variety is a complete intersection, so generated by regular sequence inside a given variety. But why this is interesting for us, in this course, we're going to derive the Serre's criterion using this theorem.
Yeah, what's if за что размерность отвечает геометрия?
Regularity?
What?
Regularity? The fact that this dimension, well, the fact that every well, the only characterization that kind of is direct is the statement that something is regular only if it has a finite projective. Every module of this thing has finite projective dimension. This is Serre's criterion. But well, if you just ask directly, what's the meaning of this? The same as in the algebra. It's just the rest of the resolution. Well, of course, if you work in general algebraic geometry, there are no projective objects, right? So you need to replace this by something. For example, you can work with the injective dimensions, or you can try to work, for example, with the flat dimensions, where you can just take resolutions by locally flat modules, which on the nice scheme is more or less the same as a vector bundle, but this is more finite ring. Right, so then we can talk about resolution in terms of vector bundles. Okay.
You mean locally free models, not locally flat. What is locally flat model?
Oh, you can define locally flat, it's just every.
Yes, both.
Hmm?
Yeah, you mean it, yeah. Locally
Yeah.
flat. Ah.
Yeah, I want to say that, no, if you work in some general situation, you don't have any nice assumptions about your scheme, you can work with locally free, you can work with locally flat, but I'm not sure that well, this is definitely not true, this is called the resolving property, that any coherent shift is the quotient of a locally free. For this you need some assumptions. But maybe it will be a little bit better, you have more chances to prove this. Maybe it's even true in my general situation, that every coherent is a quotient of locally flat.
Mm.
So anyway, so if this scheme is not nice, you have more locally flat and locally free, and I will try to find a solution with locally flat if it's not possible with locally free.
Mm-hmm.
Okay, so I'm going to separate the proof into 3 steps. So let's do the first step. Here, what I want to show is that there is element x, which is R regular, and also x is in the I, but not in the MI. Okay, so it's M, but not in the MI. Well, first I'm going to use one of the statements that I proved before, since I has a finite free resolution. But here I wrote, of course, projective dimension, but over local ring projective module of the projective module is the same as the free module, so I has a finite free resolution, and every ideal that has a finite free resolution so it contains a regular element. So we proved this when we discussed the notion of the rank in the first chapter. That was one of the corollaries that we proved.
Yeah, and the first ones that the such x exists, it's from what?
This is what we're proving in the step 1.
Mhm.
So this is kind of the statement that I want to show right now. Okay, so this thing tells me that there is just a R regular element, right? It contains a regular element. But at the moment I don't know that this x is not in the MI. So this is what I need to prove to get this improvement, which I call step 1. Okay. So first of all, I is not equal to the MI. So this is just by the Nakayama's lemma. So again, by prime avoidance, I can say that I is not contained in the MI union with the all prime ideals associated to the R. Right? Because otherwise, by prime avoidance, I would get that I is the same as MI. Right? But that is not possible. Or I'll get that I is contained in the P associated with the R, but any such P, every element in such P is a zero divisor. So that's again not possible because we have this first property already. Okay, so and another thing to notice is that here in the prime avoidance, this is of course not a prime ideal, but there's a little bit more general statement of the prime avoidance that in this union you could have up to 2 ideals which are not prime, and that statement is still correct.
Yeah, we already have it because m squared is also could be not prime, like in the last propositions. So
So what's
yeah,
yeah,
quadrant.
yeah, so So yeah, what you're saying is just that I'm supposed to make this remark earlier. First used it, yeah. Okay, so we have this. Hence we can say that there is this element x which is in the I but not in the mi, right? So this is, I'm just using that this is not a subset. And also x is not in the union of all the prime ideals associated to the R. Right?
So you say like we need at least two prime ideals, yeah?
No, I'm saying that in the union on the right hand side, say
For prime avoidance, yeah, what?
for prime avoidance, it's suppose you have some n ideals on the right hand side. Two of them would be not prime, and the rest has to be prime. So, for example, you could have just two ideals which are not prime, and this is still true. But you have more than two, all other have to be prime. Yeah, I think it's done in the notes. Yeah. So, right. So this part just immediately follows from that there's no such inclusion, but that's exactly the element I'm looking for, right? So x and the I, but not in the mi, and this is not in this union, so this is not a zero divisor. Hence, this is a regular element. So this finishes the proof of step 1. Okay, step 2. We just kind of step about linear algebra. So, before I formulate step 2, I want to fix some notation first. Let me fix some notation. Let me say that the R prime, by definition, this will be R modulo the element x that I just constructed in the step 1. And also, I prime is the ideal inside the R prime, which is I modulo x. Okay, so now I can formulate what I want to do in the step 2. So in the step 2, I'm going to show that the I prime modulo I prime squared is free R modulo I prime modulo. So I'm trying to do the induction, of course, it's usual induction by dimension, but to do this I need to choose this regular element, take quotient by this regular element, and then I need to check that these two conditions for the quotient types are also satisfied. So here in the step 2, I'm going to check that this linear algebraic condition is satisfied.
This should be R prime modulo I prime.
Yeah. Yes, thank you. Okay. Well, let x1 up to xn in the I be such that so there are kind of two types of reduction. There is a reduction modulo element x, and there is also reduction modulo I squared. So reduction modulo I squared will be denoted by bars. So x1 bar, xn bar. So such that this thing is a basis in the I modulo I squared. Right, so this is possible since we assume that this is a free module, so it has some basis. So then I claim that there are elements in the ring, so Ri in the ring R, of course I is between 1 and n, such that if I look at the difference, x minus the sum of the Ri xi, right? So since this is a basis, I take any element, so of course this x that I consider here is still the same x that I constructed on the step 1. I can kind of decompose the x bar using this basis right? But I prefer to write it not modulo I squared, but just in terms of the elements. It means that this difference is an element in the I squared.
Basis, you mean generators?
No, I mean base.
This is
Base.
free.
Yeah, so this is a free module. It has a basis. Right? So this is just saying that I can take x bar and decompose this with respect to this basis by just rewriting this and lifting this from the modulo I squared to the ring. Well, and we can also notice that m squared is of course, I squared is of course contained in the mi. So if these coefficients Ri are in the maximal ideal for any I between 1 up to n, so then, well, this element is in the mi, right? So I can move this, think this sum is again will be in the mi, so then I can conclude that the x is in the mi, which is of course not possible by our construction of the element x. So it means we can say that without loss of generality, R1 is not in the maximal ideal in this local situation, so R1 is in fact just a unit, so it's an irrotable element, right? And since this is a unit, I can as well conclude that x1, x, then x2, up to xn, well, are elements such that if I go to the bars, then this is another basis in the I modulo I squared. So what I obtained by this computation is that without loss of generality, I can always choose such a basis that this element x is just the first element of this basis. Okay. So now what I want to show, of course, is that when I consider this x2 with the prime, x3 with the prime, up to xn with the prime, then this will be a basis for this module over this ring. So for this, I suppose the following. Suppose I have a linear relation. So suppose that the sum from I running between 2 and n with some coefficients Ri prime, xi prime. So this is in the I prime squared. Or in other words, I have some linear relation, right, among these generators. So of course they generate everything. I think it's clear that if you look at the x2 prime up to xn prime, this is the generators of the I prime. So we only need to show that there are no linear relations. So here, this is the assumption that they have a linear relation. So I want to show this is not possible. So here coefficients are I again in the ring R. So I'm using the same notation, but of course there's new coefficients that have nothing to do with the previous coefficients.
So xi prime is the image of xi's.
Yeah, this is the reduction modulo x.
And there Ri prime lies in R or lies in R prime. Like if such sum is an EI prime squared, and условие на Ri, это условие на Ri или на Ri черточка? В смысле, у нас же уже новый Ri prime?
Yeah, I'm just saying that these coefficients, these are completely new coefficients.
Yes, so, but then you say about Ri.
Yeah, Ri is just an element in the R.
So not Ri prime.
Ri prime is an element in the R prime. This is the class.
А зачем там вообще это условие, то, что Ri лежит в R?
This is trivial condition. Where else it's supposed
Вы
to be?
тоже сказали.
No, we said, well, this are new coefficients. Maybe let me change notation. So let me say that this.
Мы их называем Ri prime, но потом пишем что-то про Ri, который не Ri prime. Я вот этого немножко не понимаю.
No, it doesn't work anymore. No, I'm just.
А зачем там написано, что Ri принадлежит R?
Well, because this is just some elements of why this doesn't work anymore. It looks like if your hands just a little bit wet, then this technology doesn't work anymore. Oh, maybe that was a bad idea.
А, в смысле, Ri prime это O. А, все понял.
Yeah, so if I want to formulate a linear equation, I just need to choose some coefficients, but I consider these coefficients in the modulo this element x. Okay. So suppose we have this linear relation. Yeah, then I claim the following, that there is additional element R1. So notice that here I is of course running between 2 and n. There is no R1 in this assumption, but then I claim that there is R1 such that in the ring, such that if you look at the sum of the Ri xi, now the sum is between 1 and n, then this sum is in the I squared. Is it clear that we can do this? Right. Essentially what I'm claiming here is that the difference, if you kind of leave this from modulo x to the actual elements, right? So the difference between this it will be generated by the element x, just by the definition, because it's quotient by the element x. So the difference is of the form some element R1 times x. And this is just the additional term that I added to this sum.
So there's no R1x1. There's only R1x.
Well, x1 is just x. Otherwise, it's just terrible notation. Oh, now it works. But not here. Okay. So we have this. But now, this last thing, it just precisely means that we have a linear relation for the xi's, right? If we have a linear relation for the xi's, it means that the coefficients are 0, but this is free of the R modulo I, right? So it means that the coefficients Ri that we have at the moment are all belonging to the ideal, let me say maybe, so Ri are in the ideal I for I between 1 and n. Hence, from this, if we look at the coefficient Ri prime, this is in the I prime, right? But that's exactly what we need to show. Hence, there are no linear relations. If you have a linear relation with some coefficients, then these coefficients are in the ideal, so modulo this ideal is just 0 coefficients. Hence, this is free. So I prime modulo I prime squared is free R prime I prime modulo of rank n minus 1. Okay. So this finishes the proof of the step 2. And finally, step 3, the last step. Here we're going to show that the projective dimension over R prime of the I prime is finite. If we finish this step 3, we essentially finish the proof of the theorem. Okay, let's set J to be ideal generated by the x2 xn plus I squared. Just at the moment, just annotation. Well, from this, we can easily observe that the I is the sum of two ideals. Principal ideal generated by the I plus J.
Зачем какая-нибудь, ну, типа, не зачем наказывать такого, то, что вот это будет равно проективной размерности R и, ну, потому что X регулярный.
We're going to use this definitely, but
So, an analysis about projective dimension of Ri, that is...
yeah, but wait a second. Well, what is true is the following formula. So this is what we're going to use. Is that the projective dimension of the R prime, right? Over of the of the I prime. This is the same as the projective dimension of this thing.
And the right term is less than infinity.
Yeah. So this is finite.
Kinda, we prove this carefully.
Wait. Yeah, this is definitely true, and this is definitely going to use later. I need this for the proof, but for some reason, I just think that this is not enough. Yeah, hence we need some proof for the step 3. Yeah, I think there is a little nuance here. Не, это мы точно доказываем. Это было там определенно перед формулой основы плюс.
Я просто помню, что мы точно доказывали, что если, ну там, что где плюс 1 участвует, что проективная размерность над R и U штрих плюс 1 это проективная размерность R и. Там доказывали метод факта.
Это мы доказывали, здесь нет никаких проблем. Если есть какой-то другой нюанс, я помню, что я про это подумал, и все для себя понял, но я сейчас что-то не могу вспомнить, как именно я это понял.
Ну да, вы правы. Средневосходная справа.
То есть все равно нужно что-то доказывать, чтобы это все сработало. Значить, да, формула там була не така.
Как?
Значит, да, значит, то, что вот эта формула, как написана, это вот неправильно. Да, на английском языке. So this thing is wrong. Right? So maybe I don't know, erase this or keep this to compare the formulas. The correct formula is something like this. You have the projective dimension over the r prime, right? But then the formula was for a module, right? Not for the ideal. And if I want to write this, I need to write something like this. Right? Then this thing is precisely the projective dimension of this thing, and this is finite.
And E modulo xi not equal to E prime.
No.
Why is this so? How do you see it?
The definitions are quite different, right? So here you kind of take what we say, what's I prime, right? So that was just an ideal that I obtained inside the ring R prime, which is obtained modulo x. So this is inside R prime.
So it's image of I.
Yeah, it's the image of I. Well, it's not a good what they say to think this image, because the image of an ideal is not necessarily ideal.
Yeah, but
This definition is different from this definition. These are just two different portions. This is the problem. So this is the fact this is finite. It's not important now because this thing is not equal to this thing. Okay? Do you agree with me that the right formula is correct? And we proved this before, but the left formula just compares two things that we don't know how to compare at the moment. Hence we need some computation. Now essentially what I'm going to show is that actually this I prime and I modulo xi are not very far from each other. So let me write the goal that I want to show in this proof, that I modulo xi is isomorphic to the R modulo I plus I prime. So this is the goal. Okay, so what I can notice is that the xi, so first a trivial observation, so xi is contained in the I squared. This is my construction is contained in the ideal J. So in particular, I have an inclusion that the xi is contained in the, of course it's contained in the principal ideal generated by the x, and also this is contained in the ideal J. So in fact I want to show that these two ideals are the same. So at the moment I have an inclusion in one direction. So let me take something in this intersection. So let me say that y is in the x intercept with the j. So I can write this y as some coefficient r1x, and also I can say that r1x, which is y, minus the sum I is running between 2 and n, some coefficients ri xi. So this is in the I squared.
Sum should be 2n. Yeah.
2n. Yeah. So first it's clear, and second I just take an element using this element belongs to the j, and j has this structure. So by definition of j I have this. So I claim that from this thing I can see that R1 is in the ideal I. So R1 is in the ideal I. Well, this is just by the same kind of argument as before, right? So this is some linear relation, this is a free module, hence coefficients has to be 0, but what's important for me is that R1 is in the I. Because if I know that R1 is in the I can see that I take any element y in this intersection and I can present this as a product of x and something in the ideal I. Hence, maybe one more step. Do I need one more step? Or maybe it's clear. So xi is equal to the principal value of x intersect with the g. So that's our first formula that we need. So then, if I look at the quotient of the x, ix, well, I can use the second formula that I is x plus j, so let me maybe rewrite this, x plus j modulo xi. Now this will be the sum of the x modulo xi plus, now it doesn't write, plus j modulo xi. Okay. Well, but now, since we have this computation that this I plus j modulo xi, if I consider modulo xi, then the intersection will be 0. Hence, for these two modules, this is not just a sum, this is a direct sum. So this is the composition into the direct sum. And let's look at the second sum, g modulo xi. For the second sum, I can keep g, and let me write this xi again as the intersection of the x and g. So then I can apply the what's called second or third isomorphism theorem, depends on what counting you prefer. So this will be the ideal generated by x plus ideal j modulo ideal generated by x. Right? But x plus j, this is I. So this is I modulo x, hence this is I prime. So this identifies in the formula that I want to derive, identifies the second summand as I prime. And also, I think it's relatively clear that if you look at the quotient of the x modulo xi, then this is isomorphic to the r modulo I. Well, so this is since x is a regular element, you can have a canonical map from the r to the x, right? And the image of the ideal I inside R is exactly xi, so these quotients are isomorphic. Hence we have what we want. Let me maybe write this one more time. I modulo xi is isomorphic to the I r modulo I plus I prime. Okay, so now I know, as already was mentioned, that the projective dimension of this quotient over r prime is finite. Hence, if I have a direct summand, it also has a finite projective dimension. So, projective dimension of the r prime, the I prime, is finite. And the finish of the proof is straightforward. If you know that you take a quotient by a regular element, you get an ideal generated by the regular elements by the induction hypothesis, right? Then the ideal itself, I, has to be generated by a regular sequence. So I'm going to say that this is the end of the proof. let's take 10 minutes break.
Где мы использовали, что проективная размерность конечна в предыдущих двух шагах?
Ну, у нас есть, в общем-то, еще база индукции, да? Вот я проделал индукцию, но я, ну, здесь если такой формально, можно сказать, что база индукции это будет что-нибудь типа, не знаю, как звучит ситуация. Ну, и ситуация будет такая, наверное, когда, ну, формально говоря, пусть у нас размерность, ну, ранг и по и в квадрате, да, ранг над r по и, это просто 0.
Да.
Да. Ну, тогда мы из этого делаем вот что и порожденной регулярной последовательностью, но как просто нулевой регулярной последовательностью.
Да.
В общем, это не очень поучительно, может быть, поучительнее было бы что-нибудь типа, ну, что эта штука, не знаю, имеет свободный модуль ранга 1, да? Ну, тогда более-менее, в общем, база индукции, это был бы просто шаг индукции, да. Ну, сейчас база индукции, это был бы просто шаг 1 доказательства, да. А там нужно иметь конечную свободную изоленту, чтобы сказать, что у нас есть регулярный элемент. Ну, вообще, чтобы изолировать регулярный элемент. Вот в этом месте нужно.
Мы же доказывали, что есть регулярный элемент, если просто finite representation.
Нет, там не было написано FFR, Finite Free Resolution, а не Finite Representation. Не.
То есть нам нужно для минимального, для регулярного элемента целый резольвент?
Да. Ну, если вы посмотрите на доказательства, ну, как бы, любой модуль там без всяких регулярных элементов имеет, ну, как если это нетного кольцо, да, модуль, конечно, порожденный, у него есть, конечно, свободное представление конечного ранга, это очевидно просто. Но это ничего не говорит, что резолента будет конечным. Конечным, бесконечным. Поэтому там не будет представления, там не резолента. Ну да, если как бы формально смотреть, интересно, то что ответить на этот вопрос.
Да.
Ну и можно как бы, не знаю, попытаться доказать просто для одного элемента, как базу индукции, там он тоже ровно потерпящий понадобится. Доказательство, он, на мой взгляд, довольно простое, так, если подумать. Просто оно такое длинное, какие-то линейные алгебры в середине, как надо проделывать.
В общем, неверно, что если есть модуль с конечной проективной размерностью, я взял под модуль какой-то в нем, то он тоже имеет конечную проективную размерность.
Ну, конечно, нет. Ну, можно построить идеалы. Ну, где возьмите любое кольцо локальное метро, которое не регулярно. Возьмите в качестве модуля само кольцо, проективная размерность 0. Возьмите в качестве подмодуля просто максимальный идеал. У него нет конечной изоленты, потому что у него был конечная изолента, конечная изолента была мука, и кольцо было регулярно.
Что было бы, если была конечная изолента?
Если был у M, да, вот этот подмодуль, который мы рассматривали, была бы конечная изолента, ну, как бы M, ну, короткая точная последовательность M, RK, да? У M конечная изолента, значит у K конечная изолента. Если у K конечная изолента, кольцо регулярное. Ну, тут мы докажем, прям, то есть держим сразу, это препятствие называется. Поэтому любое нерегулярное кольцо, вы где берете в качестве модуля само кольцо, в качестве подмодуля максимальный идеал, будет вот это играть тому, что вы сказали. интересно, кстати. Снова возвращаюсь к сумму. Я уже раз говорил, что в прошлый раз я помню, что надо переставить любое начало и конец раздела по движению бокса, когда это упрощается там, на несколько страниц вычислений. Интересно, что он он доказывает критерий Снера, по-честному, довольно тяжелое доказательство, а потом еще один из консенсуса доказывает в конце выхода. Хотя можно этого не делать. Но вот Блюз и Херст этого не делают, они выводят писали из консенсуса, как я сейчас буду делать.
Хорошо. В принципе, из вот этой вот теоремы у нас просто ее можно проверить максимальному идеалу, там
Да.
одно сразу
Да,
выполняется. И все.
да, теорема с консенсусом. Ну, там, если и это максимальный идеал, там вот это условие, второе, потому что и поиграть свободно,
Математически, когда вот как раз получается, если регулярный, то это кажется, там это эквивалентность, да, получится, то что
я
теорема
получится. Ну, конечно, исторически было совсем не так. Там Сэр доказал свою теорему, 55-й, может быть, а у нас 169-й. Я поэтому ничего не дату не указал, что там примерно 15 лет позже.
Я все там прям сложно доказательство, такое вычисление.
Да, ну просто не нужно 62 года.
Сейчас, по-моему, вот в Эйбеле, тоже есть теорема, там это просто такой несколько таких приятных теоремок. Но, в принципе, там доказательства каждой из теорем не сильно большие. То есть, это правда, там это более-менее доказывается всю главу, там вот это вот что-то 4, кажется. Вот. И там...
Теорема Снера?
Да, то, что там вот у нас... сейчас скажу. Буквально то, что там локальное кольцо это регулярно, только тогда, когда глобальный размерность меньше бесконечности. И в этом случае там типа глубина, размерность, ложная размерность, глобальная и коллективная размерность поля, все равно. Там такая теорема.
Это такое следствие.
То есть это следствие. А как теорема критерий разлучить?
Сейчас все закончится. Через 2-3 минуты я начну правильно двигаться. Но там, видимо, длинно, потому что он как раз по пути просто все это и будет. Там глубину, скорее всего, там будет.
Да.
Поэтому получается длинно.
Ну,
Мне вот там как-то нравится больше всего через восконсенсус. Люблю Сахерца, как это сделано. Мне кажется, все равно теорема интересно.
Она сейчас, просто, как сказать, для максимального идеала это понятно. Для максимального идеала она хороша. А вот просто так она встречается в жизни, то, что у нас и по и квадрат свободный. Это частое явление.
Во-первых, в обратную сторону это просто очевидно, что если его сопровождено регулярной последовательностью, то и в квадрате его свободно.
Да.
Поэтому это всегда так. То есть, если это просто утверждение про то, что если у вас есть полное пресечение вот этих доказательств, у вас довольно неплохо устроен нормальный пучок. Это на самом деле просто реально.
Сейчас, это в другую сторону как раз, то, что вы сейчас сказали.
Да.
Вот в эту сторону.
Наоборот, так как в определенной степени характеризация с помощью пучков освоений до того, что у вас многообразие является полным пересечением.
Да.
По-моему, это сам к себе дорога.
Это правда.
Почему в другую сторону очевидно, что если и порожден регулярной последовательностью, то и по квадрат свободен?
Мы же доказывали там даже больше, что там, если есть квазирегулярность, то там весь выбор это просто поменяние кольцо. В данном случае это просто компонент степени 1.
А проективная размерность конечна в этом случае? Или... не обязательно.
Проективная размерность. Я думаю, что не обязательно. последовательностью, да, то тогда R имеет конечную свободу элемента, которая просто как происходит в этой последовательности. Да. Это означало тогда, что если бы у I была бесконечная коллективная размерность, то у RPI должно было быть бесконечно. То есть это противоречие.
Почему у РПИ бесконечное было?
Ну, потому что, опять же, I вкладывается в R, фактор RPI. Соответственно, если вы утверждаете, что у I бесконечное, то как бы приписываете еще R, получается бесконечную изоленту для RPI. Бесконечно получается бесконечную коллективную размерность для RPI.
Можно еще раз, что мы берем? У нас РПИ.
Давайте уже говорю. Вот это. Да. Теперь, если бы оказалось, что у I нельзя найти конечную изоленту,
Да.
вот, это означало, что у RPI тоже нельзя найти конечную изоленту. Ну, просто вот она. Вот какая-то изолента, да? Соответственно, добавляете еще один член, строите изоленту RPI.
У меня резольвента В, а потом я... А что это за член?
Это, ну,
Да.
ну, как
да.
бы, не знаю, P0 отображается на I, да, соответственно, I вкладывается сюда, у вас P0
Да.
отображается сразу на I.
Да.
То есть вы как бы можете соединить, добавлять еще R от начала резольвента. И вы построите тем самым резольвенту для R по I бесконечную.
Да.
Ну, и как бы если здесь нет конечной изоленты, получается, что у R по I тоже нет конечной изоленты, а она есть.
Да.
Ну, так, в принципе, это у нас там просто можно линейно точно последовательность развернуть и сказать, что если бы у RPI была конечная свобода изолента, то у R и так далее.
Потому что пространство писать неравенство для коллективных размерностей.
Ну да, тоже.
Okay. So before throwing away the Serre's regularity criterion, let me give a definition, of course. I want to define a global dimension. I think we have discussed this before. So let R be a ring. Then the global dimension of R. So the notation is, well, there are of course different notations, but as usually I'm choosing the shortest notation, so I'm going to write GL of R for global dimension. So this is supremum of the projective dimensions, well, where M is module over R. So this is quite general definition. The ring is even not necessarily commutative. Now the ring is not commutative, potentially you can define for this thing for the left modules and for the right modules. So there are two notions of global dimension. In commutative case, of course, there is no such problem. Here I have a little lemma. Again, I'm going to leave this as an exercise. So let R be a ring. So essentially, the lemma is saying that here I take all modules, but I can just as well restrict my attention to the finite and generated modules. So the following are equivalent for some number n, which is not negative. So first, projective dimension of m is less or equal than n, and this is for any R module m. Two, projective dimension, so condition is the same. Projective dimension of n is bounded above by n, but this is for any finitely generated. So for any finite R module m. So the difference between conditions is only this finitely generated being for m being finite. So 3. The injective dimension of n is also bounded by n for any 4. So essentially what we want to show is the equivalence of conditions 1 and 2. Of course, 1 trivially implies 2. But the other points in this lemmas kind of hints how we can do this. Because if you try to go directly from 2 to 1, maybe it's not so easy to do this directly. So the last condition 4 is that the x with the index n plus 1 between m and n is 0 for all our modules m and n. And if you do this in the right order, the proof is quite simple exercise. Okay, so theorem, maybe I've learned by this one, another way it works. Theorem. This is Serre's criterion of the regularity. So let Rm be a local Noetherian ring. Then the following three conditions are equivalent. So first, R is regular. Second, global dimension of R is finite. And third, projective dimension over R of the residue field K is finite. Okay, so let's see what we need to show. Well, I think we still need to say something to prove that 1 implies 2. Right, so let's say that D is the dimension of this ring R, and let me say that N is the syzygy with the index D of the module M. So M is just any module. I can take finitely generated module. Yeah, let's say that M is finite R module. Right, I want to show that this M has a finite projective dimension. So I take the syzygy with the index D, right? So first of all, we know that N is maximal Cohen-Macaulay. There was such an exercise, I think, the second assignment. Right? It was quite easy exercise, just application of the depth lemma. So this is maximal Cohen-Macaulay, and then we have trivial case. If n is 0, we are done. Right, so the syzygy with this index is 0, hence we have a finite free resolution. So the other possibility is that this is non-zero maximal Cohen-Macaulay module, but then I have the following claim that every regular system of parameters, say x underlined, which is x1 up to xd, is a maximal n sequence. Right? Let's maybe leave this for discussion for a minute. Let me just finish the proof. And then projective dimension over R of the n. We know that this is the same as projective dimension of the R modulo this sequence of the n modulo this sequence. Right? But the R modulo this sequence is just a field. Right? So this is just a finite dimensional vector space over a field, hence projective dimension has to be 0. So even if we have syzygy at this position, necessarily, not necessarily, this is just a projective module. Hence, we can stop at this position and get a finite free resolution, or projective or free, doesn't matter, or in the local situation. Yeah, so let's return to this. If I have a regular system of parameters, do you see how this is a maximal n sequence? Or any maximum Cohen-Macaulay module. Well, we can try to give a direct proof, but we can just use one of the facts that we proved for Cohen-Macaulay modules. Remember that we proved the statement that the sequence is a regular sequence for the Cohen-Macaulay module if you take a quotient by the sequence and the dimension drops by the correct number, precisely by the number of elements in this sequence. But of course, in this case, this drops precisely by the right number. Right? We have elements which is the dimension. If I take a quotient of the n by this thing, I'll get just something zero dimensional.
And why would you get something zero-dimensional?
Well, if you take a quotient, say of r by the sequence, this will be just k. Right?
Yes.
So, but this thing is just say tensor product of n and this residue field k. So it is supported on the maximal ideal only. So this is zero dimensional. Or finite length if you wish. Okay. So this is 1 implies 2. Now, of course, 2 implies 1 is clear. There's nothing here to prove, just to take a particular module. And finally, the non-trivial part is that 3 implies 1. Well, sorry, 2 implies 3 is clear. Of course, the non-trivial part would be in the Serre's treatment of this theorem that 3 implies 1. But if you have Vasconcelos' theorem, it's actually also straightforward, right? So we have m modulo m squared is 3 k module, which is of course trivial since this is just a fine dimensional vector space. We know that the projective dimension of the maximal ideal is finite, right? For this we just look at the short exact sequence m r k, right? And since we know that projective dimension of k is finite, projective dimension of m also has to be finite. What else do we need? Yeah, so the conditions of the Vasconcelos theorem are satisfied, hence we can conclude that m is generated by a regular sequence, and then also use one of the theorems that we proved in the beginning of the lecture. Okay, so that's the end of the proof. It was quite easy if you already proved the previous theorem. And corollary, maybe 2 of those. If R is a regular local ring, then RP is also a regular local ring, and this is for any prime ideal P in this black R. So I'll formulate this for local situation, but using the standard fragment that we already done twice for Cohen-Macaulay and Cohen-Stein, if you start with not necessarily local, but any regular ring R, then any localization is also regular. So the proof of this thing is quite straightforward. I just look at the projective dimension over R of the R modulo of P. Right? Hence, this is one of the modules that has finite projective dimension. So this is finite. And then, well, it has some finite free resolution, and you can just localize this finite free resolution at the prime ideal P.
And why it is finite?
R is regular.
Global dimension is less.
Yeah, so for any module that's finite, in particular for this quotient module. Yeah, so it has R modulo P has some finite free resolution, and we can localize this finite free resolution and then conclude that the projective dimension over the localization of the R modulo P localized is also finite, right? But by the exactness of the localization, this thing can be identical we see that for the RP, condition 3 of the Serre's theorem is satisfied. Hence, RP is regular local ring. Yeah, I think historically maybe I also need to make this remark. This was the first situation, maybe in commutative algebra, maybe in general in algebra, where you can start with a ring, get interested in some property of the ring, for example, being regular, right? Formulate without any modules, and then use this theory of modules to prove something about rings. Here, for example, this implication that the localization of regular is regular is using category of modules over this ring. It's not a direct proof.
So it's kind of like from Marita equivalence, we can deduce some things. Like if we know that regular ring Marita equivalent to some ring, we know that this.
Yeah, but this is kind of more advanced story. I understand that. What I'm saying is that this theorem was the first indication that it's useful to study category of modules over rings. Maybe historically, definitely one of the first indications that studying modules is useful. Okay, corollary 2. Maybe I'll leave this as an exercise. If Rm is regular local ring, then on this global dimension is not just an additional invariant, but the global dimension of R. This is the same thing as the dimension of R, and also this is the same thing as the projective dimension of the residue field. So let's say that this is one more exercise. Okay, and I want to go to the next section, normal domains. Normal domains. And the first thing that we're going to show is again another theorem by Serre. So this is Serre's criterion of normality. Okay, so let's, as usual, so let R be in a theorem domain. Then R is normal if and only if we have the following two conditions. So first, if the height of some prime ideal P is equal to 1, then the localization Rp at this prime ideal is discrete fluctuation ring, which is just another way to say that this is a local Noetherian ring, which is regular of dimension 1. Local Noetherian ring, but maybe even better, regular local ring of dimension 1. So, DVRs have many different definitions. This is one of them. 2. If prime ideal P is associated to the R modulo X, where X is some element, so for some X in the R which is not equal to 0. So remove 0 from the ring. Okay, so So if P is associated like this, then the height of P is equal to 1. So maybe this is not the way you, if you know serious criteria of thermodynamics, maybe this is not the way how you formulate these conditions 1 and 2. There are conditions Rn, Sn, this is supposed to be R1 and S2, but I'm going to formulate these conditions and see that they're equivalent to these two conditions later. These two conditions are the most convenient for the proof.
And also, third criterions of normality usually not only for the base.
Yeah, but this is the essential part of theorem anyway. The general theorem would be just if you have a normal ring, you can decompose this as a product of normal domains. So. Okay. Okay, so first of all, yeah, so this is in two directions, so let's go in one direction. So we assume that this is normal domain. Let's show that the conditions 1 and 2 are satisfied. I'm claiming that actually it is enough. It is enough to show that if P is associated to the R modulo X, then localization is dvr. So if you can prove this claim, we've actually proved conditions 1 and 2. Let's see, do you see that this is enough?
Why for any prime ideal of height 1, it's dvr. So not any prime ideal. Or
Yeah, so essentially it would be enough. I think you mentioning the correct thing, that it would be enough to say that if you have ideal of the height 1, right, then it's necessarily of this form associated to this element. If this is true, then precisely these two conditions are exactly this condition. But if you have ideal of height 1, right, then, for example, the localization is one-dimensional ring. It has one parameter, right? So by usual commutative algebra arguments, you can think without loss of generality that these parameters of the form x in the ring over 1, and then this P is associated to this ring. Right? Maybe let me mention this as a comment in parentheses. So height P is 1, and then there is parameter, let's call this x, in the PRP. So this is parameter. So the depth of the PR modulo x is equal to 0. Right, there is only one parameter, the rest are just zero divisors in the ideal P. But we proved that if the depth is 0, again, essentially by prime avoidance, that the P is associated to the R modulo x. Okay, so let's prove this first sentence. Well, first of all, without loss of generality, I can do localization at P and assume that I have a local situation. So let's say that RP is local Noetherian domain and dimension Okay, so P is associated to the R modulo X. Well, hence,
Why do you assume that the dimension of R is equal to 1?
I don't really need this. Yeah, so P is associated. Now I just want to use kind of straightforward definition of associated prime. It is P is annihilator. So P is annihilator over the ring R modulo X of some Y. Now, of course, I'm supposed to write the class of Y, but let me abuse notation and just write element Y. So let's say Y is an element in the ring R. Okay, so then I have a couple of easy observations. So P annihilates Y, right? So it means that from the point of view of the ring R, that the YP is contained in the X. This is the first simple observation. And of course, this second simple observation that the Y, so ideal generated by Y, is not contained in the ideal generated by X. Right? So this second thing, it just means that Y is not zero element, right? So in the if prime ideal is associated, this annihilator of a non-zero element, Y is not zero. This is just trivial. Okay, from this,
So isn't Y should lies in R quotient X?
what?
Y should lies in R.
Yeah, I was saying that here, so I'm kind of taking the class.
Uh-huh.
So if you want class of Y, was too lazy to write it. But I want to think about the element Y as an element in the ring. Okay, so from this, I claim that YP is not contained in the XP. So this is probably the most important part of the proof, to show that the conditions that we have imply that YP is not contained in the XP. Right? Well, otherwise I'll get the following. Right, so if I know that YP is contained in the XP, I can just as well write this as the Y over X applied to P is contained in the P. Another way to formulate this, but P is a finitely generated module, right? So we can, from this, we can conclude that the Y over X is integral over R, but R is normal.
How we can put this?
Well, if you, for example, go back to the Atiya McDonald's book, or my notes posted on the Google Drive, there are several ways to characterize integral elements. One of them is that you can find a finitely generated module such that this element is preserving this finitely generated module. So it is in the notes. So Y over X is integral over R, and hence R is normal, hence I can say that the Y over X is in fact an element in X, in R, but that's a contradiction, right, with this condition. If this is in the R, then ideal generated by Y is contained in the ideal generated by X, which is not possible. Yeah, so this is the end of the proof of this implication. Okay, now to finish this, we choose T, which is the YP, and T is not in the XP. And we can do this. what we can say for such t, if you want to write this a little bit more explicitly. So first of all, t is some product of the y and pi, and also product of the unit and the element x. So let me write where everything lives. So pi is an element in the primary ideal P, and unit is in the R star, of course. Okay, so I have t in the y and p, so it necessarily of this form. So this is the first equality, but still yp is contained in the ideal x, right? So it has to be presented in the form some element of the ring plus, times element element x. Right? So this is always true. Well, the only maybe non-trivial claim here is that the u that I can choose to be a unit. Right? So this why this is a unit?
Well, because if it will be not unit, then yp is lies in, then t is lies in xp. No, у нас по максимальному.
So if this is not the unit, then if this is not the unit, that's necessarily the maximal ideal, right? And u is maximal ideal, which is p, so it means that t is of the form xp, which is not possible. So u is
Can you repeat, please? Can you repeat, please? Why?
So why u is a unit?
Yes.
Yeah, so suppose, we have this some element here necessarily from the ring. Suppose this is not a unit, this is a local ring. So if this is in the maximal ideal, then
Yes.
the maximal ideal is p.
Yes.
So we write t as a something in the in the p times x,
Yes.
which is not possible.
Yes.
Okay. So finally we have the following: y p is contained in the ideal generated by x, and the ideal generated by x is contained in the product of the y and the ideal generated by the p. Y, right? Just combining what we proved together. But this is the domain, so we can just cancel y and get that the p is contained in the principal ideal generated by p. But of course, this principal ideal, since p, since this not p pi is contained in the prime ideal p, the reverse inclusion is clear. So we have this equality.
So yeah.
Yeah, I was thinking that there was this condition. Yeah, okay, I don't need this condition. Yeah, so we have a local Noetherian ring such that the maximal ideal of this local Noetherian ring is generated by one element. Right, so then this is necessarily a regular ring, and dimension is equal to 1. So that's the end of the proof in one direction. Yeah, and for the DVR, I just, maybe you know this terminology, maybe you don't. This notation with the pi is quite standard, and this generator of the maximal ideal of the DVR is called uniformizing element, because any other element, even in the ring of fractions, so like some unit of power times this pi to some power, integer power, if this is in the ring of fractions, or non-negative power, if this is in the ring. Okay, let's go in the other direction. So we're going to show that the R is the intersection of the organizations Rp over the all prime ideals of the height 1. since such localizations RP are discrete variation rings, yeah, dvr for height b is equal to 1 and interception normal domains is the normal domain.
DVR is normal.
Yeah, so I'm using that the DVR is normal, and I'm also using that the intersection of normal domains is normal.
Yeah, but why DVR is normal?
Is there an elementary proof that the DVR is normal?
Yeah.
Well, I guess I was saying that you just use this uniformizing element, right? You say you have some x in the Q of R, where R is dvr. This is kind of a remark. Right? So then you can write this as some unit, and also pi to some power R, where R is integer. Well, but in particular, if you have this explicit structure, even for fractions, in particular for the elements of the ring, you can immediately see that this is unique factorization domain. And any unique factorization domain is normal. So for DVR, this is not really hard to show. And I think there are definitions of the DVR that's kind of use this normality as part of the definition.
Why is the intersection of RP for all P of height 1 is equal to it is a standard fact?
No, this is something that we're supposed to prove here. I'm just saying that if I can prove this, since I have this, I'm done with the proof. So what remains to show is that this equality. Yeah, and of course, inclusion in one direction is clear, right? Since R is contained in any of such localizations, R is necessarily contained in the intersection. So this we have for free. Height P is equal to 1. Condition is height P is equal to 1. So this is clear. So what remains to show that they have inclusion in the other direction. Okay, so let's take non-zero element F, which is in the intersection of the RPs. I want to show that actually this F is an element. So I can think about this F, of course, as the, so everything lives in the wrinkle fractions of R, right? Every localization, the intersection, also everything inside the Q of R. So F is just some fraction that lives in the Q of R. I want to show that F is in the wrinkle R. Okay, so as a fraction, I can write this F as, say, y over x. And now the key is to consider module n, which is the quotient of the ideal generated by the x and y by the ideal generated by x. So if I can show that n is 0, I'm done, right? Because it means that I can, that these two ideals are equal, right? In particular, it means that I can express, for example, y as some element in the ring times x. So this fraction will be just an element of the ring. So the goal is to show that n is 0, but the way we're going to show this is a trick that we used before. I'm going to show that the set of the associated primes is empty. Okay. Well, we can notice, first of all, that this module n lives as a submodule in the R quotient by x. quite easy observation. Now, if I have a prime ideal P associated to the n, well, since we know that prime ideal associated to the submodule associated to the module, hence we can say, so then P is associated to the R modulo X. Right, then by the second assumption we can say that the height of P is necessarily 1. So height of P is 1. Yeah, and so this associated prime, so let me say that F is an element in the RP. Right, since F is in the intersection for height 1, this is height 1, so F is in the RP. So F is in the RP. Yeah, so any associated prime has necessarily the height which is equal to 1.
Why F is in RP?
Well, because the height of P is 1. Right? And we choose F to be in the intersection of all the localizations for all right ones. Okay, yeah. So this we have. Okay, so then so F is in the RP, right? But F was the fraction y over x. So I can say that y, which is just the F and x, so x is in the ring, hence this is in, well, the right hand side is in the RP. Right, so then, and of course the left hand side is also in the RP, so this is in the RP. Okay, so what it means, right? It means that the second generator y can be expressed in terms of the first generator x. Hence, this ideal and this ideal are the same, right? In the localization with respect to. So the conclusion is that the NP is equal to 0. Right? But I think we're done here, because I take any associated prime, I necessarily see that this associated prime has height 1, and then I also see that the localization of my module at this associated prime is 0. Hence there are no associated primes, because they all has to be height 1, but such height 1 primes are not even in the support. It can be associated. So the associated primes of n is empty, so the module n is 0, and this means that the y can be written as the r times x, so this f is actually an element of the ring. Okay. So this is the kind of the key part of the Serre's criteria. There is a way to refine with this. I also want to note is that the proof in one direction, when they prove that something is DVR, yeah, I think that was essentially what you need to do in the problem in the second assignment. So when you want to show that the dimensional normal is Homological, okay, I give you a solution for this problem.
Yeah, but the problem is finished.
Yeah, but that's the point. I wanted to schedule this carefully to prove this theorem after the deadline of the second assignment. Okay, so now I want to introduce the general conditions. So there are conditions which are called, maybe I can formulate this as a definition or notation, I don't know. Let me say this is notation. So we have conditions Rn. Just saying that the ring is satisfying condition Rn, maybe R1, R0, or for some specific number. It means that the following, that localizations Rp are regular, so this is regular for any p such that the height of p is less or equal than n. So this is condition Rn. So for example, all Rn's are satisfied if and only if the ring is regular. And there's also a condition, Serre's condition Sn. So both conditions Rn and Sn are called Serre's conditions. So R is for regularity, now S, maybe this is for Serre, maybe not, I'm not sure. So this means the following. This is conditioned for a module, and the condition is that the depth of the MP is at least the minimum of the n and dimension of the MP. And this has to be true now for any prime ideal in the spec of R. So condition Sn can be formulated for modules, and of course it makes sense to ask this for rings also when m is equal to R. Okay. So then, another way to formulate Serre's normality criterion, so let's call this theorem. So in a theorem ring, is normal if and only if it satisfies R1 and S2. In fact, the heavy part of the proof I've done in the previous theorem, if you think about this, you realize that this is just kind of restatement. You want to understand the conditions 1 and 2 from the theorem, that these are R1 and S2. So I leave this as an exercise. So in particular, we have corollary, not even from this theorem, but from the previous theorem, that if R is a regular local ring, then R is normal. Right. Clearly, for regular thing, all Rn's are satisfied and all Sn's are satisfied. So, for example, all Sn's are satisfied. This means that the module is Cohen-Macaulay.
Yeah, Sn for any module or for what? Or there exists such one?
You mean in the theorem? Yeah, so if I don't specify the module, it means that this is just condition for the ring.
Uh-huh.
So R1 is satisfied and S2 for the ring for R. Okay. That's all I want to say about the normal domains. So let me go to the unique factorization domains. So the main goal of this part is to show that any regular local ring is a unique factorization domain. Well, first I want to, probably you know this statements. I think it's even part of the standard course. So in a theorem domain, R is a unique factorization domain if and only if we have the following. For any prime ideal such that the height of this prime ideal is 1, and there is f in the ring such that this prime ideal is generated like this. So this is ut if and only if any height 1 prime ideal is principal. Do you know this statement? Have you seen this before? Okay. If you haven't seen this, maybe I prove it. The proof is quite easy. I want to say that if you go in one direction, so you know this is unique factorization domain. So we take element x in this given prime ideal of height 1. Of course, I want to assume that x is not equal to 0. Then, since this is unique factorization domain, I can decompose this uniquely as a product of irreducible elements. So, xi's are reducible elements for any index I. Well, since now this is a prime ideal, I can claim that there is an index I such that xi irreducible element is contained in the prime ideal P. Well, just let's say that the principal ideal generated by this xi is contained in the prime ideal P. Well, but this is also prime. Okay, so one of the ways to characterize unique factorization domains, this is definitely in the core algebra course, is to show that the element is irreducible even only if this element is prime. So this generates a prime ideal, just another way to say that the element is prime. But now I claim that it means that they have to coincide. Right? Why they have to coincide?
Height of 1.
Yeah, by the dimension reasons. The height of P is 1, and we have the unique minimal prime ideal. This is a domain, so there's 0, and xi is not 0, so it has to coincide. Now let's go in the other direction. So we want to show that any irreducible x is prime. To show this is unique factorization domain. So suppose P is minimal prime over the given element x, which is irreducible. So by the gross height theorem, I can claim that the height of P is equal to 1. Right, so, and now I know that any height 1 is generated by some element. So this P is generated by some element y. So in particular, the element x that I consider is the product of the y and z, and x is irreducible. So this implies necessarily that the z has to be a unit, otherwise this is kind of non-trivial decomposition of irreducible into another product. And if this is just a unit, it means that the ideal generated by x and ideal generated by y are the same. And so ideal generated by x is prime, but it should just be, so x is prime, end of the proof. Okay. Definition. So now I want to introduce the notion of divisors. So let R be in a theorem domain. Theorem domain. Regular. In codimension 1. So if you studied while divisors before, you know this is standard assumption. Which is precisely means that the localizations Rp are DVRs for any P such that height P has codimension 1. Height, we can think about this height as a codimension. So codimension 1 is this condition. Regularity codimension 1 is this condition. So this is the assumption on the ring R. So then the free abelian group generated by primes of height 1 is called the group of Weyl divisors. So the notation for this is div of R.
So we need to prove why this is free abelian group, yeah?
No, this is definition.
Or just the set of prime ideals and generate free abelian.
Yeah, so if you take this set and just take a free abelian group generated by this set. So the typical element is something like this. You have coefficients and P and this P. So the sum is a finite sum. And well, I don't know, maybe I need to introduce some index to formulate the next condition. So say Ni Pi, this is finite sum, and the height of all these Pi's are equal to 1. So there are also some terminology. For example, if you consider just P, right, so there is such element in the div R, right, just a linear combination where we have one coefficient 1 and nothing else. These are called prime divisors. Prime divisors. And also there is a condition where just terminology. So if you can write this D as a sum, say of the NP and D is greater or equal than 0, sometimes it's also called effective. Well, this is just means that all the coefficients that we have here are non-negative. So this is for any P that we have in this sum. Okay. Now I need the following thing. If I know that this localization at the prime ideal of height 1 is discrete valuation ring, I have an actual valuation. So there is mu P. This is a map from the Q of the RP, but I can as well just identify this with the Q of R to the integers. Right, since we know that we have this uniformizing element pi, this valuation is discrete valuation is easy to define. This, you present this element as unit times p to the r, so this valuation of the unit p to the r, this is just r. Well, yeah, so it's not clear what you're supposed to put when the element is 0, right? So to avoid this situation, I'm going to put star everywhere. So this valuation is only defined on non-zero elements. Okay, proposition.
Can't we just take 0 to 0?
Well, this is not really consistent with the definition. This is 0 is supposed to be a unit, not a zero element.
Like that.
Usually people say that the valuation of 0 is infinity, but then you need to extend this z by one more element to infinity. I just don't want to do this. So let f be in the Q of R with a star. So then the valuations that we have are almost all 0. Right, so this VP is 0, except finitely many prime ideals of height 1.
Там разве не такие вещи называются, ну, то есть проект можно построить там дивизор, вот разве не такие вещи называются простыми дивизорами? Слушай, это может путаю.
Нет, это называется главный дивизор.
Главный.
So let's take this fraction. Let's write this as x over y, right? So it's x and y being some elements in the ring R. So if the evaluation mu p of x is not equal to 0, so then we can say that the R modulo ideal generated by x, and then we localize this at p. This is not 0. Again, just think in terms of the uniformizing element. So this p is in the support of the R modulo x. And we also know that the height of this p is 1. Right? So the height is 1. Hence, p is minimal in this support. Right? In this support, we don't have elements of height 0. So elements of height 1 will be minimal. But minimal elements in the support are the same as minimal elements in the associated primes. So in particular, minimal elements in the support are all associated. So the conclusion is that the P is associated to the R module.
There's no prime ideal of height 0.
Well, this is still a situation of a normal domain.
Yes.
There is only one ideal of height 0, namely the 0 ideal. So if you take this module, and localize this as the 0 ideal, this is the same as taking tensor product with the Q of R. But clearly such tensor product is 0. Okay, so P is associated to this thing, but everything is not even finitely generated, so the set of associated primes is finite. Hence, end of the proof. Okay, so another definition. In this section, there are mostly definitions of devices. So if we have some fraction f, which is not zero fraction, so q of r with a star, we can associate the divisor with this function. So div of f, this is by definition the sum over all primes of height 1 as usual. So I compute the mu p of the f and multiply by. So by the previous proposition, this is a finite sum, so the definition makes sense. And we can consider this as an element in the group of the wave divisors. And it also more or less clear, maybe easy exercise, that the div as a map from the Q of R with a star to the divisors of R, this is a group map. Just do this quite easy. So it maps product of functions to the sum of the divisors. And finally, the most important part, so the orthogonal of this map div is called the the divisor class group, and the notation is CL of R, or CL for classes. So we also have a canonical map that I'm going to call C for class. This is from the divisors of R, or canonical map to the co-kernel. Okay. So proposition. Let R be a normal domain. Well, at this point, I guess you all know that all my rings are Noetherian, so of course it's Noetherian. So in these assumptions, if I take f to be in the Q of R with a star, non-zero fraction, so then the two conditions are equivalent. That the divisor of f is effective if and only if element f is not just a fraction but element from the ring. Okay. In one direction, I will say that this is clear. Right? If you have element which is not in the, not a fraction but just element on the ring, clearly by construction, this thing is non-negative, effective. So in that direction, it's also not very hard. So in that direction. So we have here is that the variation at the prime ideal P of height 1 is not negative, so this is any P such that the height of P is equal to 1. But this means that F is in the RP for any P such that the height of P is equal to 1. And since this is true for any such P, F is in the R, since R is the intersection of all this. Yeah, I didn't mention this, maybe it's important to notice that this formula that R is the intersection of the all localizations at height 1 ideals, this is true for any normal domain. It was kind of appeared in the proof, but of course, maybe I should have formulated this as a corollary that there is such formula for any normal Noetherian domain.
So like we can say this proposition that f, divisor of f is effective if f in integral closure of R for any domain. Yeah.
Well, that's another story. I don't want to even introduce notion of the divisor for a non-normal ring. So
no for domain, for Noetherian domain.
yeah, which is not normal. And I'm saying that I don't want to do this. I only, well, it is possible, and the problem is that there are possibilities many ways, and we need to discuss what way is correct for what we want. I just don't want to go in this direction. Okay, so from this we have corollary, and I'm saying that we have a short exact sequence with the 4 terms. We have 0, we have R with a star. This is just all invertible element, well, units in the R. Then we have Q of R with a star, all non-zero elements here. Then we have div map to the divisors of R. And then we have this class map C to the CL of R. So proof. Well, let's see. Well, we already know almost all exactness, right? So, for example, this is just by definition the map of the co-kernel. So we actually, without this term, this is more or less by definition, right? So the only thing that we need to check is that the, well, of course, this is in the embedding. This is quite clear. So the only non-trivial exactness is right here. at the QR star. The rest is just obvious. Okay, so let's say that the divisor of some fraction f is equal to 0. So f is an element in the Q of R with a star. Okay, so this means that the variation at the prime ideal P is equal to 0, and that is true for any prime ideal of the height 1. Well, in particular, we can conclude that this is in the RP with the star. Again, for any prime ideal such that the height of this prime ideal is equal to 1. So, in the other direction, we know that this element will be in the ring R, right? Exactly by this argument. But if f is not a unit, so then there is a prime ideal P such that the height of this prime ideal is equal to 1, and and then I can take an element inside this prime ideal. Let's call this f. And then this is not a unit, right? An element of the ring. I can just take a minimal prime P over this f. The height of this by the group height theorem will be 1, so this is correct height, and f is contained in the P. But if I have this gives me that the valuation is positive for this element at this prime ideal.
Why f is you prove that f should be unit.
Yeah, so I'm saying that if this is not a unit, it is not possible to have diff f equal to 0. So that's the end of the proof, and it looks like there soon will be exam here, so perhaps I don't want to hurry, so I just prefer to finish at this moment and continue next time.